Welcome, ladies and gentlemen. In this video, I will present our paper, Model-Driven Application Development for Evaluation and Optimization of Automotive EE Architectures. First, I will motivate our work and introduce the general scenario. After that, the toolchain, as a part of which the presented application was developed, will be described. Next, I will explain the major implementation details regarding the visualization of EE architectures as well as subsequent analysis. Finally, the performance of the presented application will be discussed before the results of the published research is concluded. For a long time, the development process of automobiles was dominated by enhancing the performance of its mechanical components. Due to the advancing digitalization that affected almost every aspect of our modern world over the last decades, new sorts of requirements within the automotive industry have emerged. By today, things like safety features, comfort features, and, more relevant than ever, pro-environmental measures have a significant influence on modern automotive design and development processes. Cars have become complex cyber-physical systems composed of electronics like sensors, actuators, and electronic control units, which form the functional backbone of these so-called electronic systems. The components are connected within a communication network that consists of various different kinds of bus systems. With advancements in technology, the complexity of such EE systems increases continuously. A single modern car may, by now, contain more than 100 different control units, not to mention sensors, actuators, and other electronic components. This results in new challenges concerning efficiency and cost-effectiveness, which demand for suitable evaluation and optimization methods for EE architectures. To be able to handle the increasing complexity, model-based approaches have been established for the design and development of automotive EE architectures. Within this process, different vendors created a variety of tools and frameworks for different scopes of the design and development process, which may be more or less incompatible with each other. A major challenge today is the development of flexible and consistent toolchains for tool integration. As part of a research project, the Systems and Software Engineering Group at the Technical University of Ilmenau develops a workflow together with an integrated toolchain for model-driven analysis, evaluation, and optimization of EE architectures. This paper presents one of the central applications of this toolchain as well as the conceptual approach on how we designed and developed such integrated tools within this context. Therefore, the scientific contribution of this paper is an approach for mastering the addressed challenges using model-driven techniques. The goal is to improve reusability and interoperability of such applications for evaluating and optimizing EE architectures, and thus simplifying the development of integrated and easily extendable toolchains based on uniform metamodels. The scenario of the presented application is one of the central optimization problems in automotive design, the so-called deployment problem. It describes the challenge of finding a good architectural mapping between logical functionalities and physical computation devices which should execute these functionalities. The choice of such a mapping from a potentially large design space can of course have a great impact on efficiency and cost-effectiveness measures of an automotive design. Such mappings can aim for a variety of optimization measures. For example, the number of required control units or overall cable length, which concern cost-effectiveness, as well as the mean power consumption or load balancing of communication buses during operation, which concern efficiency. For this paper, we assume an altered version of the deployment problem, which is finding optimal communication paths between ECUs which run related logical functions based on an already existing architecture. The toolchain, as a part of which the presented application was developed, is based on the software Prevision by Vector Informatic. Prevision is a widely used proprietary software for model-based EE engineering in the automotive industry. In contrast to that, our application is based on the open-source Eclipse Modeling Framework and the Obeo Sirius project, which is a framework for developing graphical model editors. For a model-driven toolchain, we do of course require an explicit metamodel. In contrast to related work, we did not want to introduce our own meta model for automotive EE architectures. We rather decided to utilize the MOV-based meta model provided by the already well-established Prevision software. This meta model was extracted from the software and translated into an EMF-compliant eCore meta model via model-to-model transformation. On the basis of this meta model, it is possible to create EMF-based applications, for example for visualization, analysis, or generation, based on concrete architecture models created in Prevision. These models are obtained using query and selection mechanisms and subsequently transforming them into EMF-compliant models using model-to-model transformation as well. Now let's look at the implementation details of this highlighted action. The first bundle of functionalities of the presented application is data reduction, selection, and visualization. First, a type-dependent reduction is performed. As the meta model contains over 4,000 meta classes, it is necessary to filter the types that are actually required for visualization within the proposed use case. Let's have a look at an excerpt of the meta model. On the level of logical architecture, we are basically looking at logical functions, which are connected via so-called logical assembly connectors. Regarding the proposed use case, it is sufficient to visualize only logical functions. On the level of hardware architecture, we are looking at electronic components like ECUs or active stars that can be connected via different bus systems. As we are interested in visualizing and later on analyzing hardware topologies, such electronic components as well as the bus systems that connect them should be visualized. After this first step of pre-selection, a context-dependent data reduction is performed. Keeping in mind that automotive architectural models can easily contain hundreds of electronic components, bus systems, and logical functions, it is obvious that a context-specific selection has to be applied before being able to provide a suitable visualization. Of course, in most of the cases, we are interested in analyzing only specific aspects of the whole model, for example, the context of a specific feature of the vehicle. In the presented application, this context is user-defined. The user selects a so-called anchor element, which in our case is a logical function that we are interested in. Based on that, the application determines all logical functions that are connected to the anchor function on the logical level, which means functions that directly interact with the anchor function. In the meta model, logical functions are mapped to process units, which are subcomponents of an ECU. That way, the concrete model can be queried to retrieve the ECUs that run the anchor function as well as connected functions. The foundational issue that drives the proposed use case is that while we observe only directly connected logical functions, these functions might run on ECUs which are far apart from each other on the hardware architecture level. As the goal is to determine optimal communication paths between such devices, we need to visualize all possible communication paths which exist in our defined context. To do so, the application implements an adapted DFS algorithm and traverses the hardware architecture that is defined in the model to find all possible communication paths between the pre-selected ECUs, which means intermediate devices as well as bus systems. While doing so, the application stores already traversed elements in adjacency lists to avoid circles. If a path between the source and target ECU is found, the intermediate elements that were previously collected are saved. After termination, all retrieved elements are stored as an internal graph-like data structure, which can then be visualized and further processed during analysis without having to traverse the whole hardware architecture of the model again. This figure shows the visualization of an excerpt of a test model after the previously described steps. In this case, the logical function window coordinator, which runs on ECU body module, was selected as the context or anchor function. So the logical function as well as its corresponding ECU are highlighted. Note that ECU powertrain module also runs the window coordinator, so redundant instances of the context function are also taken into account here. The remaining logical functions are the ones that directly interact with the window coordinator and are visualized within the ECUs they are running on. All other devices as well as bus systems, for example the body CAN bus, were retrieved using the previously described traversal algorithm. Besides the model visualization, the application offers additional functionalities like a properties view for selected elements, as well as a toolset containing various tools. It is possible to add or hide existing components of the model in case the context of the analysis should be altered beyond what the application automatically does. It is also possible to create new elements like ECUs, bus systems, logical functions, or connections. At the bottom of the toolset, we can see the analysis section. This brings us to the next step after visualization, the proposed communication path analysis. When the path analysis tool is selected, the user is prompted to select the target function within the context. As an example, one could choose the function pWinControlFP running on ECU pWinFP. That means that the user requests to find optimal communication paths between the ECU's body module and pWinFP, which run the context function and the target function. To achieve that, an adapted Dijkstra's algorithm is performed on the internal graph structure mentioned earlier. For simplicity reasons, the weights of all edges are defined as 1 in this example, which means that shortest paths are literal shortest paths in terms of hops here. Of course, other weighting functions are possible. These could be based on, for example, mean load of bus systems or mean energy consumption, as well as mean wake time of adjacent ECUs. The optimal solutions are highlighted in orange. In this example, the application suggests to route communication directly either via the pWin-Lin bus or the body CAN bus. The second best solutions, highlighted in yellow, suggest that it would also be possible to route the communication over intermediate ECUs. That means that different possibilities are provided so that the user can also take other measures like load balancing into account. For performance evaluation of the presented application, a set of 3 test models based on a prevision demo model as well as a reference model was created. These test models are gradually decreasing in size as the granularity of the pre-selection of elements in the model increases. The first one, Test Model Complete, contains the complete EE architecture of the demo model. The second one, Test Model Comp Packages, contains only context-relevant components of Test Model Complete. For Test Model Context, an additional selection of context-relevant elements inside the pre-selected components is performed. That means that functionalities that shall not be observed are filtered out. The last model, Reference Model Use Case, is an excerpt of a real-life automobile model provided by our industry partners. Thus, it contains a much larger and much more complex architecture than the demo model. As the first measure of performance, we assess the execution times for the initial build-up process of the internal graph, which is done by the DFS traversal of the hardware architecture described a few slides back. On the left, we see the measured execution times of the DFS traversal per model. As a reference, the table on the right shows the number of electronic components and bus systems per model. Looking at these numbers, one could intuitively expect a linear growth of the execution times. This is obviously not the case. Note that the y-axis is scaled logarithmically. During the performance evaluation, we could observe that the required time for traversal depends substantially on the number of bus systems contained in the models. We explain this with the amount of complexity that an additional bus system can potentially add to the traverse topology. As a bus system links all connected components with each other, it can be thought of as a complete graph. Thus, adding just a single bus system to a model with 20 connected components results in 190 additional edges that may have to be traversed. Due to that, we conclude that the number and of course complexity of bus systems in the model is the main driver that influences execution time for traversal. The second measure that was observed is the required time for the application to find optimal paths. On the left, we see the measured execution times of the path-finding algorithm per model. During the previous DFS traversal, the application maps the electronic components of the original model to a set of vertices and the bus systems to a set of edges to form its internal graph. As a reference, the table on the right shows the number of vertices and edges of the graph which the path-finding algorithm takes as an input. Additionally, the number of bus systems that were actually taken into account, because they were on possible paths between our source and target functions, are depicted. That way, we can see how many bus systems actually make up the edges of the graph. Again, the influence of the number and complexity of bus systems becomes apparent. For the shortest path analysis, though, the time complexity seems to be linear. Finally, let's conclude. In this paper, we presented an application for model-driven analysis, evaluation, and optimization of EE architectures based on the Eclipse Sirius framework. It serves the purpose of visualizing different architectural layers of an EE system as well as the mappings between them. The logical and hardware architecture of a particular user-defined context can be visualized and edited using the graphical model editor. Furthermore, these architectures can be analyzed and optimized by traversing the communication topology and finding optimal communication paths. The application can be easily extended by certain weighting functions to enable optimization regarding specific measures. A performance analysis showed that the computational complexity for visualization and analysis is not only dependent on the pure size of the model, but mainly on the complexity of the model topology of interconnecting bus systems. Adding more bus systems to the model which connect a sufficient number of devices can drastically increase the complexity of this task. This especially affects the implemented DFS algorithm, which initially traverses the whole topology to find all possible communication paths between specific devices. The computation time for the shortest path analysis shows a linear behavior compared to the size and complexity of the initial hardware topology. Compared to the DFS, this algorithm works on a much smaller and already preprocessed representation of the original topology. Thank you for your attention. If you have any questions, feel free to contact me using the provided email address. If you are interested in a detailed explanation of the complete model-driven workflow of our research project, which I addressed earlier, please also refer to Dr. Ralf Maschotta's paper Model-Driven Aspect-Specific Systems Engineering in the Automotive Domain. For further information about our work, please see the link below. Goodbye.
Thanks for your presentation. I have two questions, but I'm sure we have a lot of additional ones. First question from Avi. Did you consider Capella for capturing the architectural and aesthetic with your visualization? Is there any constraint or limitation?
So I can answer that question real quick. By now, no, we did not consider Capella yet. But I mean, especially concerning potential constraints and limitations, I think this could be an interesting question for the future.
Nice, thanks for that. Just mark it answer. Okay, it's done. Next question from Cédric Brun. Besides the analysis you demonstrated, do you think the model could be used for other activities, generate document or validate other aspects, for instance?
Yes, we are actually doing that within this whole process that I described. So this editor software is actually just a part of a bigger workflow. So for example, we use the models that we extract from the prevision software and transform them, for example, also to generate simulation models for MATLAB, for example, to do, for example, validation or simulation of dynamic behavior. So we also do that, yeah.
Thanks for that. And well, another question from Sid. Okay. I'll go back to the answer question. Yes, how much effort was for building such a tool?
Well, how should you measure the effort? Of course, when starting the whole thing, it was, for example, pretty complicated to get to know this whole automotive meter model. For example, as I said, it contains something like 4,000 meter classes, which are structured in different layers, which have references between each other. So, for example, you have the pure logical layer, you have a software layer, so which maps conceptual logical functions to software components. Then there is the hardware level, which maps on the one hand the logical layer as well as the software layer to the hardware components. So getting to know all that was pretty complicated. But I think your question, with your question, you were more or less interested in building the Sirius tool. Well, it depends. The difficult part, or let's answer the second part. What was hard is actually was the whole processing stuff. So it was relatively easy to implement the pure visualization stuff, to create the nodes and the connections, etc. But doing that whole DFS and Dijkstra's algorithm in the background was more or less tricky. But of course, as Sirius offers this feature to use Java services in the background, it was a solvable problem. What is actually something that was, let's say, or does not really work by now, as it is really hard, is some process of an automatic layout or arrangement of the nodes. This is something that is pretty hard to do. It's not like maybe in some other graphical frameworks where you have like a canvas and you can say something like, okay, put this node at position X something, position Y something relatively to each other. That is actually something that is really complicated and that we are still trying to solve, actually.
Okay, thanks. Okay, next question. For clarification, do you assume a fixed component to an SAU mapping and focus on an optimization of the communication? Is there a tool supporting the analysis of communication?
I'm not really sure if I understand that question right. So the ECU, so the mapping between the ECUs and the logical functions is fixed based on the automobile model, for example, that is provided by an industry partner. So that is more or less fixed from the beginning. And then the question is, okay, can this be optimized in some way? For example, let's say you have two logical functions that interact with each other very, very often, which means if one logical function is invoked and the corresponding ECU is working, most of the time the other ECU of the connected function will also be working, and they will have to communicate with each other. And the communication, of course, has to be routed over intermediate components, which all have to be activated, have to be woken up from some kind of standby mode, and then, of course, will consume energy, which is especially a bad thing for electronic cars, for example. So the question is then, okay, maybe can we optimize this architecture in some way, for example, that we put the two logical functions that have to communicate with each other very often on ECUs that are not too far away from each other in case of intermediate hops, so that we can maybe save some wake time and respectively energy that is consumed by the intermediate nodes, in a way that we put them close to each other.
Okay, thanks. And I've actually also a question. What is the acceptance of this tooling by your industrial partner? Is it used by Lambda engineer or specific profiles?
Could you repeat that, please? So,
what is the acceptance of such a tool by your industrial partner?
Currently, I'm actually not really aware of what they are actually doing with it. So by now we are still developing it. We are still developing this whole process. But actually, it was something that they demanded beforehand. So hey guys, we have that deployment problem. There is not really a nice standardized way of automating this whole optimization process. Guys, think about something. We'll pay you. So actually, I think that they like it, and maybe if we put some more effort in it and extend it by some functionalities, I guess that will be accepted.
Okay, and so does it mean that you use the representative data or just, let's say, academic one in your presentation?
We actually use real automotive models from the industry partner. Of course, we as I said, we pre-select the data and we filter it because these models are really huge, and so we actually, for this academic purpose, we focus on specific functions as a case study, so to say. But we actually use real automotive models.